Okay, good. So thanks to the organisers for the invitation. It's been a really fascinating conference. I'm just going to talk about theoretical aspects of really a very general question. What limits a species range? And ultimately, a species range has to be limited by its failure to adapt. It's a trivial statement. Why don't species expand their niche to occupy a wider range of environments? And of course, this can be for the trivial reason that there's a hard physical limit. A fish can't climb out onto the land very easily. So Craig Moritz's high elevation species that we heard about this morning, when they get to the top of the mountain, there's nowhere else to go. Conversely, there can be rather complicated situations involving interactions amongst multiple species, and there we probably can't say anything very general. It's a very case-specific problem. What I want to do is focus on, I think, a rather simple situation where a species range is limited by its failure to adapt simply to the physical environment. And here we have a real puzzle, because our experience with quantitative genetics, with artificial selection on virtually any population, on virtually any trait, is that if we have a reasonably large population and if we select for 50, 100 generations, we can shift by many, many standard deviations. We can produce extraordinary changes, as of course we see with domesticated plants and animals. And yet we often see sharp edges to a species range set by the physical environment, a failure to adapt to incremental changes where one can see no obvious obstacle. And the question is, why is that? Why is there this limit to adaptation? And one possibility suggested by J.B.S. Haldane a long time ago is that there is an effect of gene flow from the abundant central range of a species out to the margins, which prevents adaptation to marginal conditions almost by definition, by rather rare populations. There's a conflict between gene flow and adaptation, and we've heard about this in various examples in the last couple of days. So what I'll do is talk about two sort of very simple theoretical models which really try and get at the essence of the problem. One is simply asking, when can a new population get established in a new environment as a result of one or a few individuals coming in and adapting to the new conditions and expanding into that new habitat? And secondly, I'll be looking at adaptation along a continuous gradient in which the environment is changing at a constant rate in space, and nevertheless the species may be limited to adapting only to some fraction of that potential range. And in both of these cases, I'll be trying to see whether we can find some rather simple predictions, some rather general predictions, which could be related to quantities that, at least in principle, could be observed, could be measured. So keep in the back of your minds that although this is a rather abstract, very simplified model, I'm trying to focus on what sorts of things really matter, are important, what would we like to know about natural populations to be able to predict whether or not species can or can't adapt. So first of all, establishment of a new population in some new environment. And we're imagining that migrants come from a source population with some genetic variability. We'll focus on simply the genetic component of variation in some trait. And the trait we focus on could actually be a composite of many different features of the life history. What really matters is the growth rate in the new habitat. So we can imagine, in an idealized world, we could measure the rate of growth of different genotypes taken from the source population in this new environment, and typically those rates of growth will be negative. The population could not establish itself without some change, without some adaptation. And we define the fitness of an individual in the new habitat as e to the power beta z. Beta is a measure of the strength of selection, the relation between fitness and this trait z, which is a surrogate for all the things that affect growth rate in the new population. And I'll use a very, very simple model, but a very powerful model called the infinitesimal model, which really comes out of animal breeding work, which simply says that we forget the genetic details. We forget about exactly what the genetic basis of the trait is. Provided that there are large numbers of genes of small effect, then to a very good approximation, at least in the short term, and it's the short term we're concerned with here, offspring will simply follow a normal distribution around the mean of the two parents. So two parents cross, they have a certain trait value, the offspring are distributed around the mid-parental value, and crucially the variance within families, the genetic variance within families, is a constant value, roughly half the total variance in the population, and it will be reduced to the extent that the parents are related, are inbred. And of course inbreeding is a crucial element in understanding the establishment of a new small population. So we say that recombination, sexual reproduction, release variation amongst the offspring are distinct from each other, we have sexual reproduction, and the extent to which that variation is released depends on the relatedness of the parents. If they're unrelated, then we have this fixed quantity determined by the hidden genes of small effect segregating. So if we look at this model, we actually only have two parameters, and the most important parameter is actually the divergence between the source population and the new population. The distance that has to be travelled measured in genetic standard deviation. So imagine an individual comes in, let's just look at this left-hand picture to start with, and that individual has a value measured in standard deviations, genetic standard deviations, let's say -2. It's 2 standard deviations away from where it has to be having a positive growth rate. So the value of 0 here is a special value, a threshold, above which the population can grow. And these different lines show the probability that a single individual can establish. I'm, of course, having to assume that self-fertilization is possible. I have this very simple-minded model where individuals mate at random with each other, including with themselves, but one can modify that without too much trouble. So what's the chance that a single migrant individual can produce offspring that are a little bit better, grandchildren that are a little bit better, that eventually will take off and will establish, increase their trait value, increase their growth rate, get established? And that probability depends very strongly on the number of standard deviations away from this threshold, rather obviously. But interestingly, the second parameter, this beta parameter, which measures the steepness of the fitness gradient, the steepness of the relation between trait and growth rate, that has rather less effect. Here we have a rather shallow fitness gradient, here we have a rather steep fitness gradient, changing by a factor of 8, in fact, between these different lines, a factor of 2 between each successive line. That makes relatively little difference, particularly out here. What matters is just how many standard deviations do you have to go. Now that's talking about the chance of establishment of a single individual producing genetically variable offspring. If we go to the right-hand plot, it's a bit confusing, but if focus here, these solid lines are simply copying the most extreme lines here, and we're looking now at the probability of establishment on these dotted lines here. You can see that, yeah. These dotted lines show the probability not of an individual with a certain trait value, but of a random individual from the source population, which may be good, may be bad. So we now take a random individual, which may be plus, may be minus, and ask what's the chance that this random individual gets a population established. And now it can be quite a few standard deviations. Now we're plotting here the mean in the source population. The source population can be 3, 4 standard deviations below the threshold. Virtually no individuals in that population actually above threshold. But nevertheless, a particularly good individual can get established, can produce better offspring in future generations. The population can take off. So these upper dotted lines here, showing for 2 different values of the fitness gradient, not making a huge difference, that we can get some appreciable probability of establishment, depending crucially on the numbers of standard deviations you are from threshold. Okay. So, let's look at the magic clock. Yeah, I'm doing okay. So, we can also ask here a sort of question, how do we separate out the effects of chance and the effects of selection? And one way of doing that is to say, let's suppose that these individuals coming from the source population, although they vary in phenotype, and vary in genotype, their offspring are identical to them. They're completely homozygous, the offspring are identical. There's no scope for evolution or adaptation. And that's then shown by these lower dotted lines, which shows, if you like, the probability of establishment simply through random draws from a normal distribution. And there is some probability, but it's much, much lower. So the difference between these pairs of lines and these pairs of lines tells you the contribution of adaptation. The combination of adaptation plus random chance allows a population that's maybe 3 or 4 standard deviations away from the threshold to nevertheless found a new population, let's say a new host race exploiting a new host plant. Okay. So now we move to ask what happens when we don't have just one individual, we have a number of individuals coming in. We have a rate of immigration at a rate m per generation. So we have a Poisson number of migrants coming in, averaging M per generation, M individuals. And this has two contrasting effects. One is that having multiple individuals coming in, which can mate with each other, which are not related to each other, boosts genetic variation. And in fact, if the number of migrants coming in is more than around 1 or so, you can maintain very high genetic variance in this small founding population. But on the other hand, the migration is also pulling the new population back, is pulling the mean of the population back towards the source, preventing adaptation. So there's a conflict. And in fact, there's an intermediate level of migration that gives the greatest probability or the greatest rate of establishment of a new population. And this is summarized in this diagram here, where we're plotting the expected time it takes to establish a new population. It'll happen eventually, against the numbers of migrants on a log scale. So we're going from 0.01, very low migration rate, up to 1, up to 10 or 100 migrants per generation. And then this solid line here is the rather trivial lower bound. Let's imagine every migrant immediately founded a new population. Well, that's the fastest possible rate of establishment. We're going to be a long way above that. It takes longer than that. The dotted lines here show the extrapolation from the previous slide. What happens if we have single migrants coming in at a very low rate? Then eventually there's some chance, just 1 over p, 1 over the probability of establishment, of getting a new population. But as we increase the migration rate, we get these interaction effects coming in. And the effect on the whole is actually to slow down, to reduce the chance of adaptation, to reduce the rate of establishment. And the crucial parameter here again is the numbers of standard deviations away from the threshold for positive growth. And these different lines show that different numbers of standard deviations. This line here is 1 standard deviation away, not much divergence, not much need to adapt. As we go up, we go 1, 2, 3, 3.5 standard deviations away. And of course, the more standard deviations you have to move to get to a positive growth rate, the longer it'll take to establish a population. And this is a log scale, so up here, it's essentially going to take forever. So there's a threshold behavior, which means that if the divergence is less than about 2 standard deviations, or 1.5 standard deviations, down here, more migration means faster establishment. And if you have enough migration, it'll happen very quickly. But there's a threshold above which more migration actually slows down the process. If divergence is more than a couple of standard deviations, then migrants are actually pulling the new population back, and however much migration there is, actually that swamping effect dominates, and it's impossible to establish a new population. So we have a kind of threshold which depends on a single parameter, essentially, which has, in principle, a sort of concrete, measurable status. You could imagine, although it would be extremely hard to do, thinking back to the first plenary talk, which in both, in principle, you could measure growth rates and genetic variation in growth rates and establish just how far do those have to shift to establish the new population. Okay. So I'll move now onto I'll move from a single population onto a continuous decline in the environment. I've had a few comments about polygenic versus discrete allele adaptation, but I think I'll skip those. Let's talk about the continuous decline work. Yeah. And this goes back to work I did with Mark Kirkpatrick quite a long time ago now. Check the time. In which we looked at a very simple model again of adaptation along a linear environmental gradient. So we imagine that there's an organism living in a linear habitat with a constant carrying capacity in principle, constant quality along this habitat. The dispersal rate is sigma. Sigma is the distance moved, typically from one generation to the next. Strictly speaking, it's the standard deviation of distance between parent and offspring. And then we have stabilizing selection on some trait, which favors some optimal value. So at any point, fitness declines with distance from the optimum. And that optimum varies linearly with distance. So the crucial parameter here is this little b, the rate of change of the optimal trait value per distance. And so we summarize all this by saying that there's a fitness, a growth rate, which has some positive value, which decreases with population density, so we have density regulation in here, and which decreases with deviation from the optimum. And Vs here is a measure of the allowable range of deviations after which fitness decreases. So 1 over Vs is the strength of stabilizing selection. So we have a very simple model with not too many parameters. And what we found was that the answer depended, the outcome depended, on really 2 dimensionless quantities. And with lack of imagination, we call them A and B, right? So this big A is a measure of genetic variance. And in fact, it's a measure of the loss of fitness in the population due to genetic variation around the optimal trait value. So having a large value of A is bad for the population in that it means that many individuals have a lower fitness than the optimal value, but it's good in the sense that genetic variance allows adaptation. Okay? And so this is crucial for determining the possibility of adaptation to a changing environment. And then this quantity B is related to a second kind of load, a kind of migration load. And we can think of it as the load, the loss of fitness, due to movement from the home environment to a new environment, 1 dispersal range away. So we've said that there's a gradient, a change of environment per distance of B. So B times sigma, which is here, okay, is the change in the optimal trait value which you would experience if you move 1 generation's dispersal. And that change reduces your fitness by this amount because they're stabilizing selection. So we're measuring the loss of fitness due to genetic variance around the optimum, this is A, and the loss of fitness due to dispersal to a new environment over 1 generation, call that B squared. And we're measuring both of those relative to the growth rate of the population, R, the growth rate from low density, which, if you like, is a measure of the ecological resilience of the population. And we want to know what are the outcomes of the competing effects here, adaptation to a new environment requiring a change, requiring genetic variation. And actually the answer is very simple, and it's fairly insensitive to the details of density regulation or whatever. Basically you have 3 possibilities. Down here, if you have a high amount of genetic variance, a high load due to variance around the optimum, but rather a shallow gradient here, then the population can simply adapt everywhere. The mean is always at the optimum, and the population can extend its range indefinitely. On the other hand, if you're right up here, if you have a very, very steep gradient, then the population collapses, it can't adapt, and it goes extinct. But in between, there's quite a wide range where the gradient is sufficiently steep that the population fails to keep up with it, fails to adapt to it. And what happens here is that it can sustain a range within a limited region. And the trait mean does change along the climb, but it doesn't change fast enough. So it gets further and further away from the optimum, and the population fitness goes down, and it goes extinct. Okay, so this is telling us that if we have enough genetic variance, we can get this ideal situation of perfect adaptation. And what's actually quite surprising and a little bit paradoxical is that if you then extend the model and say, well, genetic variance isn't determined by God, it isn't a fixed quantity, it can evolve. And we put in discrete genetics, we put in various kinds of genetics. Let's say we have a whole lot of genes with additive effects, 2 different alleles at each, and we allow those to evolve, and we let the whole thing run. What happens is that almost always mixing of populations along these steep environmental gradients generates extra variability, and this is a very general phenomenon. You mix distinct populations, you generate more genetic variance. The genetic variance goes up, and it goes above the threshold needed to adapt to a wider range. And actually, in a very general range of models, the genetic variance seems to be able to evolve to a high enough level that the population can always adapt its mean to the current optimum. It may still go extinct if the genetic variance required to do that is so big that everyone's a long way from where they ought to be, but at least the mean can always adapt perfectly. So that seems, a wonder of natural selection. That's really great, but it's left out a crucial quantity, the role of random drift. And random drift introduces an extra feedback into the process that interferes with adaptation. As a population fails to adapt, it gets smaller. There's more random drift. Random drift interferes with selection in the same way that gene flow into that small population interferes with selection, and the whole process continues. There's a collapse. And so we want to ask now, to extend this deterministic model, which had these 2 parameters A and B, to ask what happens if we allow for random drift in a finite population. And this is work by Jitka Polikova, and she's really done all of this work, so I'm just kind of stealing her results here. This is sort of one example of very many simulations that she's done, in which, top left, we have the trait mean tracking very precisely the optimum across a few hundred genes. So we have a simulation with essentially a continuous population, actually for practical reasons divided into hundreds of little genes. We have selection on very many genes, hundreds of genes, determining a quantitative trait, and typically, at least in part of the range, the mean can adapt to the optimum very well. But beyond a certain region, it may collapse, and so the population size here is very high, is close to carrying capacity here, but it collapses at a certain point. The genetic variance collapses along with it. And what's happening at the genetic level, if we look at just some of the many hundreds of Kleins here, shifting from one allele to another, as we go along this gradient, one allele is replaced by another, one allele by another. So any one of those Kleins is very erratic, is very random. But together, they produce an essentially deterministic, systematic adaptation which can match the optimum very well. So when can this range extend itself and expand or contract? What happens is for any particular set of parameters, this outcome won't be stable. It'll either expand and adapt to a wider range, or it'll contract and in the end be limited to a small range or go extinct. So what happens? Well, it turns out that actually you only need one extra parameter to describe this, and this is again a rather general outcome which doesn't depend on the genetic details at all. What matters is this quantity, the product of the population density, the numbers per distance, times the dispersal rate, sigma. So this n sigma is called the neighbourhood size, or is proportional to the neighbourhood size. Roughly speaking, the number of individuals per dispersal range. And that multiplied by something which I have to admit is rather obscure and unknown and hard to know, which is the square root of the selection coefficient on the underlying genes responsible for adaptation. Who knows what that is, but it's some small number. So if the product of neighbourhood size and square root selection is big enough, relative to this dimensionless parameter b, the dispersal load, okay, if that's big enough, in fact greater than 6 times that parameter b, then the range can expand. If it's smaller, then drift erodes variation, causes a sufficient loss of variation that the range collapses. And this is summarized in this picture, which actually summarizes an enormous number of simulation runs with all sorts of different parameters. But it all boils down to a two-dimensional threshold between b on this axis, the steepness of the gradient, versus the efficiency of selection relative to drift, which is set by essentially population density times square root selection along here. If the gradient is too steep, then we have the red dots. That means the range contracts, ultimately to extinction or to a limited range. And down here in blue, we have expansion. So actually a rather simple conclusion, which depends on just these parameters. Okay, so I should be wrapping up, I guess. Just to summarize, I've said that if we think of establishment of a single population, then the outcome really depends on the distribution of growth rates, the genetic variation in growth rates in the new habitat. And if the population has to shift by more than a few standard deviations, then it's very, very unlikely that establishment can be possible. If we look then at a linear gradient, then we again have rather simple outcomes dependent on a rather small number of parameters. Adaptation to that changing habitat, spatially changing habitat, requires genetic variance. It requires that the load due to genetic variance be large relative to the load due to environmental change, dispersal across a changing environment. Given those two parameters, A and B, we can work out what happens. In a deterministic situation with a very large population size, mixing generates genetic variability, but in a finite population, drift prevents adaptation if the population size is too small. I should actually change this, I suppose, and make it actually true. It prevents adaptation if population density is too small. Okay, so we have these relatively simple predictions, but I suppose anyone who thinks about it for more than a few seconds realizes actually they're all almost impossible to measure in practical situations. It's a big frustration that we have huge amounts of data from genomic sequencing, which can tell us quite a lot about things like population density and dispersal rate, perhaps, at least in principle. But it's very hard to get from that to the things we actually care about in determining species expansion, population dynamics, which are really fitnesses, growth rates, genetic variability in fitnesses. We know what we need to measure, but it's very hard to measure those things. And I think actually we have to step back and think about some basic open questions that we have to answer before we even get to the kind of modelling framework that I've described. Questions such as, does gene flow in fact degrade adaptation? Does it in fact lead to a reduction in population size and an increase in extinction rate? And we've heard hints of that in the various talks, particularly in Christian Both's talk was a very interesting one, showing how difficult it is to actually demonstrate both adaptation and a consequence of adaptation on population size. But this is a basic question we need to know whether any of this modelling is really relevant. And then perhaps something which is a bit more straightforward, but still pretty hard, is genetic variance in traits that matter ultimately in fitness lower at range margins, or is it higher along steep environmental gradients? And that's something that could be accessible, but unfortunately not accessible via looking at neutral markers, but probably requiring hard work on the quantitative genetics of fitness components or fitness itself. So I hope that's not too dispiriting. There's hope anyway. Thank you.